I'm Valeria Korol, a postdoctoral fellow at the University of Birmingham, where I study our galaxy. And I will show you how we can map the sky with Einstein's invisible waves. So all the stars that we see on the night sky belong to our galaxy, the Milky Way, named like this after this bright glowing patch of the sky. And because we're looking at our galaxy from inside, you can imagine that it was not trivial to understand how big is the Milky Way and how it looks like from an external point of view. So in this presentation, I will overview what do we currently know about our galaxy, and I will show you how we can study it in the future. So we believe that our Milky Way is a spiral galaxy with the bar at the center. The Sun is positioned somewhere in between the spirals at approximately 30 degrees with respect to the bar. If we could look at our galaxy from side, we would see its spirals and stars in between as a luminous disk. The bar as a boxy spherical structure in the center that we call bulge. We would also see a more diffuse glow around the disk that we call stellar halo, that besides stars also contain these luminous small dense lumps of light called globular clusters. So we were able to construct this picture of the Milky Way by scanning it at all kind of ways of electromagnetic spectrum, from radio waves that are as big as a soccer field to microwaves that are as big as a tennis ball and that we use in our kitchens, going to infrared that are as big as a biologic cell and also us humans emitting them as heat, to then go to the visible light emitted by stars as our sun and that we can see, to finally get to the tiniest X-ray and gamma rays emitted by radioactive elements. So let's start from the map, the most familiar to us in visible wavelengths. This is a Milky Way map made by the Gaia satellite that is currently in orbit scanning our galaxy. And here you are looking directly at the galactic center. And you should imagine the east, west and north-south points of this map to wrap around us. And because the Sun is located at the same height as the spirals of the Milky Way and the majority of the stars, we are seeing them as a luminous disk. In front of us we also have interstellar dust that absorbs visible light, so that we see these dark patches on the map. And you may also notice these two luminous spots that we know as Magellanic Clouds, so the two closest galaxies to us. And here you see a collection of the Milky Way maps in different electromagnetic wavebands, and you can notice that in all of them our galaxy looks quite different. So let's start from radio, that is represented in these four panels. And here you see the radiation from electrons and hydrogen gas. Notice, for instance, that the gas is very concentrated in the galactic plane. We then go to far and mid-infrared that reveals cooler gas and protostars. We can then go to near-infrared and optical that shows the stellar light, and you can see the bulge at the center in both of the maps. And you can also notice the dark patches in the optical map caused by the interstellar dust that are absent in the near-infrared. Finally, at X and gamma rays we see hot gas and light generated by cataclysmic explosive events like supernova. So each of these maps showing us one of the ingredients that constitutes our galaxy: atoms, molecules, dust, stars, and so forth. And we use these maps as pieces of a puzzle to construct the picture of the Milky Way that I showed you at the very first slide. However, we are still missing a piece of the Milky Way puzzle because there are many stars that are just too dim for our telescopes. And also think about black holes that do not emit light. How would we ever see them? Can we use a different kind of waves to study invisible objects constituting our galaxy? And the answer is, of course, yes, we can use the waves of gravity, so-called gravitational waves. So let me now introduce the concept of gravitational waves and show you how we can detect them. Since school, you know the Newton's law of gravity that says that everything attracts everything else with a force inversely proportional to the square of the distance between objects. And objects respond to this force with acceleration. And this law governs the motion of planets, satellites, galaxies, and so forth. However, Einstein had a different interpretation of gravity. He imagined space and time as a giant sheet of rubber, with mass being the quantity causing the rubber sheet to bend, like in this picture. So the matter tells space-time how to curve, while the space-time tells matter how to move. For example, the reason why the moon orbits around the Earth is because the Earth is massive, causing a big distortion of space-time around it. So if you try to move on a straight line around such a big distortion, you will find yourself to actually moving in a circle. So from the Einstein's point of view, there is no actual force pulling the moon, but it is just the bending of space-time. And gravitational waves are ripples of the fabric of space-time that can be produced whenever mass is accelerating. So everything with mass or energy in principle can make gravitational waves. But because gravity is a very weak force, we need something really massive and moving very fast to make significant ripples. For example, black holes and compact stars like neutron stars and white dwarfs in binary systems spinning around each other in minutes or seconds, can cause significant gravitational waves. So to visualize this again, imagine that rubber sheet representing space-time and now put two heavy objects going around and around each other. So this produces a sequence of ripples as shown here. And gravitational waves can then propagate unperturbed through the entire universe. And while they travel through the universe, they stretch and squeeze space-time itself and everything they pass through. But the effect of stretching and squeezing is extremely tiny, so normally we don't notice it, and therefore in this video it was vastly exaggerated for you to visualize it. So how we would detect something like this? If the space between you and me is stretched or compressed, we would not notice it if we would measure it with the ruler with the equally space marked on it, because the mark would also get stretched further apart. But we can use the speed of light to measure distances, because if the space between 2 points gets stretched, then light takes longer to go from one point to another, and if it gets squeezed, then it takes less time to cross the 2 points. So this is how the LIGO experiment detects gravitational waves. It has 4-kilometer long arms, tunnels, and it uses lasers to measure the distance between the endpoints of the tunnels. So when gravitational waves comes through, it stretches space in one direction and squeezes in the other. Meaning that the length of the arms at the time the gravitational wave passes is different. So by measuring the interference at the end point where the laser bounces in the different tunnels, we can tell whether the space in between stretched or compressed, and this is with incredible precision. So this is the first detected signal that was called GW150914, where GW stands for gravitational wave and the number stands for the date it was detected. So 14th of September 2015. And this signal was generated by the merger of two black holes, and I will now explain to you why. So in this plot we have time on the x-axis, the amplitude of the waves on the y-axis at the top panel, and the frequency of the waves at the bottom panel. So let's look at the red line. You see that it follows these wiggles, and that get closer and closer to each other, and as they get closer also the amplitude increases, and then the signal suddenly disappears. So the time between the peaks here is the measure of frequency that we can read from the bottom panel. And we can see that the green color here increases from roughly 30 to somewhere up to almost 500 Hertz. And the key for understanding the origin of this signal is the duration, that was only 0.15 seconds or so. So this tells us that this was extremely small binary. As the reference, you know that the time for the Earth to complete an orbit around the Sun is 1 year. So this binary should be much, much smaller and spinning much faster. And if you do the math, you find that the size of the system should be of the order of kilometers. So the only astronomical object that can be that small are, of course, black holes. And from how fast the frequency changes in this signal, we can measure how massive these black holes are. Another point that I want you to notice is this factor of the amplitude, 10 to the minus 21, meaning that I need to take the value on the y-axis here and multiply it by 0.0000, 21 zeros to finally reach 1. So that's extremely tiny. For comparison, that is even smaller than the size of a proton. So starting from this very first event, over 5 years we now collected many more. So all the blue circles here represent binary black hole mergers, and the orange ones represent binary neutron star mergers detected by LIGO. So we now have a whole population of gravitational waves event that we can study. So what's next? And next there is a whole spectrum of gravitational waves. It goes from 10 to the 3 to 10 to the minus 9 Hertz. So we can think about these frequencies in terms of binary orbital periods. So here between 10 to the 3 and 2, 10 to the 2, we have binary spinning around each other in seconds. Between 1 and minus 1, we have binary spinning in seconds. Between 10 to the minus 3 and 10 to the minus 4 hours. And here at the low frequency end, we have binaries going around each other in years. And of course, as for electromagnetic waves, we can think about wavelengths that would represent the size of the binaries. So here we would have binaries as big as the Earth, to go to the binaries as big as the Sun, to finally get to the binaries as big as the entire galaxy. And typical high frequency systems here are binary black holes and binary neutron stars. Then in the middle we have binaries made of bigger stars like white dwarfs, But we also have binaries made of more massive black holes, so thousands and million times more massive than our sun. While at the lowest frequency end we have supermassive black hole binaries, so those that are billion times heavier than our sun. So to detect high frequency sources we are using LIGO that I showed you before. To detect bigger wavelengths we need bigger detectors, so for that we need to go into space. So we are now planning for a space mission called LISA that I will show you in the next slide. And to detect the biggest wavelengths we cannot build such a big detector, so that we need something more clever than that. And for detecting these waves we are combining signals of galactic pulsars in a network, and that is sensitive to gravitational waves. So my research focuses on millihertz frequencies that are detectable with the laser interferometer space antenna, in short LISA. LISA will fly sometime in 2030s. Its design envisions 3 identical spacecrafts in equilateral triangle configuration, and the spacecrafts will exchange lasers along the 3 arms of the detector. While the distance between spacecrafts, as I mentioned before, will be huge, somewhere around 2.5 million kilometers. So that is bigger than the size of the sun. So literally, LISA will be a giant gravitational wave observatory in space. It will follow, the whole constellation will follow a circular orbit trailing behind the Earth, and it will measure a variety of gravitational waves. So those produced by a merger of massive black holes residing in the center of galaxies. LISA will be able to see them all across the universe. It will also be sensitive to binaries composed of white dwarfs, neutron stars and black holes in our own galaxies and in the neighboring galaxies. And finally, LISA will also see black hole binaries composed of supermassive black holes with stellar mass black hole companions. And those will be extremely useful for testing general relativity in extreme regime. So remembering the maps that I showed you at the very beginning, my job is to forecast such a map for LISA, and we want to have those kind of maps ahead of the mission to understand what new we can learn about our galaxy from white dwarf, neutron star and black hole binaries that LISA can detect. So usually I start from an idea that I want to test. So here, for instance, I'm testing whether LISA can see structure of our Milky Way. For this I need a computer simulation of our galaxy, and here you have an example that very similar to what we think Milky Way looks like. Of course, there is still some modification that I need to do to make it as realistic as possible, corresponding to our observations. I place the LISA detector inside the simulation, and then I populate the simulation with binary stars. And here I light up in green and yellow those that will be detectable by LISA. So what I've learned from this exercise is that we will be able to study the structure of our galaxy using gravitational waves, and we will do it extremely well. So we will see the Milky Way bar, perhaps also the spiral structure, and importantly we will be able to cover the whole surface of the galaxy. So we will map our side of the galaxy, but also the opposite side of the galaxy. And this is, especially this side of the galaxy, is extremely difficult to reach with the light of stars. This is because of the dust, of the interstellar dust that in between us. So to give you some perspective, this is what we see now with the telescopes if we want to focus on dim stars like white dwarfs. And this is where we will see them with LISA. So in our galaxy, but also with in the neighboring galaxies. So to conclude, I want to show you my final prediction, the Milky Way map as seen by LISA. So here, as in the maps that I showed you in the beginning, you see a central bulge and the disk cutting this map in half. So in red and orange colors, you have the stellar halo in yellow. And what we found, that we also be able to see all the little galaxies around our Milky Way. So Magellanic Clouds, Fornax, Sagittarius, perhaps Andromeda Galaxy as well. So this would be a completely new way of studying our galaxy using objects that are very dim or do not emit light at all. And this is why I'm looking forward to have these new observations that will allow me to test theory about our galaxy and maybe even discover new mysteries about it. So thank you for listening to my talk, and I'm looking forward for your questions.